Next, we consider another integral I2d, which is ddl Okay, this is the integral that we'd like to calculate. Now, in order to do that calculation, we will use Feynman parametrization, and we had two identities discussed earlier in lecture 14 for Feynman parametrization, in particular this one. So we have two factors downstairs. So it's like 1 over a1 times a2. So it is this same formula with n equal to 2, and then we will have two alpha integrals, d alpha 1 and d alpha 2, but then alpha 1 plus alpha 2 should be equal to 1. So alpha 2 should be equal to 1 minus alpha 1, right? So I can get rid of this alpha 2 integral and the delta function and substitute in this integrand alpha 2 equals 1 minus alpha 1. Okay, so this is what I'm going to do. So this is gamma n equal to 2 means gamma 2. So this will be gamma 2 times d alpha 1, let me call it x here, 0 to 1, then integral ddl over 2 pi to the power d you have alpha 1 a1 plus 1 minus alpha 1 a2 to the power n means 2. So x times, so you have to identify which one is alpha 1 and which one is alpha 2. It doesn't matter. So let me take these as alpha 1, this as a1. So x times this, alpha 1 times this means x times that. Plus 1 minus x times L square plus M square. Now this, let us manipulate this, massage this a little bit. So this is 1 minus x times L square plus 1 minus x times M square plus x times L square minus 2 L dot P times x plus x times P square plus x times M square. So this minus x L square and plus x L square cancels. So I'm left with only L square here, minus 2 L dot P times x. Similarly, minus x M square cancels with plus x M square. So we have only 1 M square. So plus P square x plus M square. This is same as L minus p vector times x whole square. This will give you L square minus 2 L dot p times x plus p square x square. But I don't have p square x square, so I subtract p square x square plus p square x plus m square. This is L prime square, where L prime vector is L minus px plus p square into x times 1 minus x plus m square. Now you see, I have separated out L and P completely, and L has become, so I have an L prime square, but the relation is just linear. You know, this thing is just a shift, a constant shift. Px for particular value of x is a constant shift. So dl prime is same as ddl prime is same as ddl, and so therefore I can simply write it as this: gamma 2 integral ddl, I am renaming from L prime to L, 1 over L square plus. So what I can do now is 1 over L square plus Q square whole square, where Q square is equal to P square x times 1 minus x plus m square, right? So what I have done is, and I have written this entire thing as this L prime square plus Q square, and dl is same as ddl prime. So this is ddl prime, this is L prime square plus Q square. Then I renamed L from L prime to L, and Q square is this much, this portion. And gamma 2 is just you know, 1 gamma 1. So gamma 2 is in 2 minus 1 factorial. So now this L square plus Q square to the power minus 2 can be written as minus integral ddx 0 to 1 del del Q square of ddl by 2 pi to the power d L square plus Q square inverse. And this integral we just calculated earlier. This is nothing but d1d. And if you substitute that value, then the result is minus 1 over 4 pi to the power d by 2 gamma 1 minus d by 2. Then derivative with respect to Q square of this object is d by 2 minus 1 times Q square to the power t by 2 minus 2. And that's 1 over 4 pi to the power d by 2 gamma. With a minus sign, this can be read as 1 minus d by 2 minus with the minus sign. So 1 minus d by 2 times gamma 1 minus d by 2 is gamma 2 minus d by 2. Substitute the value of q square, which is m square plus p square x times 1 minus x 2 minus d by 2. Right, this is the result for the second integral. Okay. We shall now consider another integral, third integral. And that's given by dd L1 over 2 pi to the power d dd L2 over 2 pi to the power d. In fact, we can simply consider instead of L1 minus L2. I mean, I can send L2 to minus L2. So this will be P plus L1 plus L2. So let me write it that way. Now, of course, if you look at it, if you do the same inspection of UV divergence, then you see there is 6 powers of momentum downstairs, where there are 3 factors each having L square. So, and upstairs we have L to the power 2d. So, so it will be convergent below d equals 3, 0 to 3. And so normally one would think that we should just use the Feynman parameterization and proceed accordingly. But before introducing Feynman parameterization, we should use we shall use partial p1s. This actually reduces the degree of divergence, because partial p takes out the d equal to 3 should take out the t equal to 3 divergence, and it will extend it to higher values of d. It is after using partial p1s we shall use the Feynman parameterization. That is how the computation will go, and we will write the entire integral in terms of 2 terms, which we shall later on interpret when we do Feynman diagram calculation for phi-fourth theory. So insert one over 2d del L1 mu del L1 mu. So I am doing partial P over 2D dimensional momentum, which is basically L1 and L2 combined together. So that's why we have this identity. And so this is integral ddL1 by. So I'm writing after integration by parts, throwing away the surface term. I'm writing whatever we left with. As I argued before, the surface term will go to 0 for the same within the same region of convergence of the original integral. So each of these derivative will act on two factors. So this is L1 derivative. It will act on this factor and this factor. L2 derivative will act on this factor and this factor. And so each one of them will give you two additive terms. So total of 4 additive terms one should calculate. So let us calculate that L1 derivative. This is minus L1 square plus m square minus 2 to L1. L1 derivative acting on this first factor. This is what I just calculated, times L2 square plus m square inverse. Then let us calculate that this is the second, the first derivative acting on the last factor. Let me now calculate the second derivative, which is L2 mu dotted with derivative terms. So these are minus L1 square plus m square inverse L2 square plus m square to the minus 2 L2 mu. Inverse. Okay, and then minus so the first term that we get is this one will be 2L1 square upstairs. Below we'll have L1 square plus m square. So this is 1. Then we write this term so this term comes with the first term that we just wrote comes with a negative sign, and there's an overall negative sign. So I get no sign here. Same is true for the term that I'm going to write now, which is this one. This also has a negative sign here, and that cancels this one. So I should have 2L2 square divided by L1 square plus m square L2 square plus m square whole square. Then the other two terms, this one and this one, so I have made a mistake here. This is -1 because this one has, the next one has -2. The derivative acted on this factor. So for these two terms, second and fourth term, we have the same denominator. And in the numerator, I have this factor to be same, but they are dotted with two different vectors. This one is L1 and this one is L2. So it is 2L1 plus L2 dotted with P plus L1 plus L2. And downstairs we will have L1 square plus m square L2 square plus m square, p plus L1 plus L2 square plus m square square. Now all these three terms have all of them have a factor of 2, so which cancels the factor of half in front, and so the sum of these three terms can be written in the following way. So I have taken some of the factors from here, the common factors in the denominator, and keep them outside, and then within the bracket I will have, you see, the first term has L1 square plus m square to the power 2 here. The second term has a second factor to the power 2, and the third one has a third factor to the power 2. So I have taken one factor from each of these. So I will have L1 square by L1 square plus m square. So within bracket, L1 square by L1 square plus m square. Then the second, L2 square by L2 square plus m square. And the third will have L1 plus L2 times P plus L1 plus L2, okay, divided by this factor. Now the quantity in the numerator, which is this, I shall write it in by breaking it in two pieces, so which I will write P plus L1. I have to write L1 plus L2, which I will write as P plus L1 plus L2 minus P. So P plus L1 plus L2 square minus P dot P plus L1 plus L2. That is how I'm going to write. So it is P plus L1 plus L2 square divided by P plus L1 plus L2 whole square plus m square minus P dot P plus L1 plus L2. Now, the another manipulation that I will do in this step is as follows. which is I add m square upstairs every term, right? And then subtract m square by this, then m square by this, and m square by this. But when I add m square, those terms, each one will become 1. So that will be 3. So 3 minus m square 1 upon L1 square plus m square 1 upon L2 square plus m square. Now this term, constant term 3, this coefficient of this is this integral, which is the original integral. This is the original integral. And therefore, we write 3 divided by d I3 of t minus 1 over d then here I again multiply this factor with this individual factor and write 3 terms. So there will be a total of 4 terms, but the last term is p dot something, but these ones are this factor multiplied by this individual factor. So that will be like going back to the previous form, and there's a reason for that. L1 square plus m square to be minus 2, L2 square plus m square to be minus 1, p plus L1 plus L2 square plus m square to be minus 1. There's a factor of m square outside, so let me write it here. Plus m square then we shall now see that these 3 terms, this one, and this one are actually same, because I can shift each L integral by arbitrary amounts. That is the reason why I can give proper shifts and show that they are same. And to do that, you can write it this way: 3 by d, like 3d minus 1 over d. What I would do is, wherever we have that factor 2 minus 2, I will make a shift in the corresponding momentum such that this factor, so this is L2, so this factor becomes L1. So if it has to become L1, then I should replace L1 by L1 minus P minus L2. So L1 minus P minus L2 whole square plus M square to the minus 2. L2 square plus M square to the minus 1. L1 square plus M square to the minus 1. Right? Let us check if I've done right. So let us call this L. If it is L, then L1 must be L minus P minus L2. L1, this is L. So L1 is L minus P minus L2. So I substitute it here. So this is L minus P minus L2. But then L integral and L1 integral will have the same measure because it's a shift. So I rename L to L1. This is what I have done. Similarly, we do the same thing for the second term. In this case, the power minus 2 is occurring with L2. So I want to make this L2. So if I have to make this L2, then I should shift. I should write L2 as L2 minus P minus L1. Sorry, I have done something. Sorry, I have written it wrong. So this is L1 square plus M square minus 1. I'm writing this line by replacing L2 by L2 minus P minus L1. I'm writing the third line without any change. Now let us see if these three terms are same or not. The factors which have powers -1 are same, because L1 square plus m square minus 1, L2 square plus m square minus 1. Here also L1 square plus m square minus 1, L2 square plus m square minus 1, and the same thing here. Only the -2 power, that factor, the momentum changes. It is L1 minus P minus L2. It is L2 minus P minus L1. It is P plus L1 plus L2. Now I can always, since it's a square, I can flip the sign. So if you flip the sign, then it will become P plus L2 minus L1. This will become P plus L1 minus L2. So these two terms will be having minus L2 and minus L1, where we have both plus L1 and plus L2 in this term. That is also not a problem, because L2 and L1 both can be sign of both can be flipped, because it's a symmetric integral. So these are all both of these can be replaced by P plus L1 plus L2, and hence same as this term. So therefore we can write this this result as so here I'm going to write the form. It can be written as 3 by d I3 of d minus 1 over d 3m square times k p plus p mu k mu of p, where this 3m square kp is basically, so this is this first 3m square kp, so m square is there, and 3 times, and the rest of the integral is kp. So kp is given by integral d L1 by 2 pi to the d L2 by 2 pi to the d times L1 square plus m square, L2 square plus m square. And the last term is p dot something, so that is p mu k mu, and therefore k mu of p is given by now the same integral, same expression can alternatively written as minus half del p mu of another integral dd L1 over 2 pi to the power d dd L2 over 2 pi to the power d times L1 square plus m square L2 square plus m square plus L1 plus L2 plus m square. Okay. So now combining all these results, what we can write now, see, we have started out with calculating I3 as this integral, and then we have shown to be this expression, to I3 to have this expression where I3 appears here as well. So we, just like before, we take all I3 on the left hand side and show that I3 is given by 1 over minus 1 over d minus 3 times 3 m square k of t plus P mu K mu of P. So what we have done here is that from the original expression or integral expression of I3, we know that this has singularity at d equal to 3. So the region of convergence is 0 less than d less than 3. And we don't know how this expression will behave at d equals to 3 and beyond. So what we did is, using partial P method, we have extracted out this divergence as a pole at d equals 3. Okay, that's the progress we have made. And now we have Kp and K mu P given by the two expression here and here. And this involves these integrals, which we can now perform using Feynman parameterization. Okay. So I have done 2 slides.